presenter is Amal Gueroudji, or I think that I pronounced it okay. She is from Argonne National Lab, but originally from Algeria and from Superior Studies in France. And her presence here is through our good friend, Professor Ian Foster from Argonne, who approved the funding for the trip in a record 35 seconds, meaning that would be a good idea. Yeah, that's it. And people say that academia has no execution speed. And Amal has been here last year, so that's it. Now, silly jokes apart, that's what we try to do here, support new blood, new generation of researchers, industry. And I thank you for coming again.
Thank you for having me again. I will be talking today about high-performance computing workflows, which I called contemporary workflows, and the challenges we're going to have, or we're having right now. So as we all know, computational workflows have been the backbone of modern discoveries in multiple domains, either through high-performance simulations, machine learning trainings, data analysis coming from instruments, inferences, and so on. And these are just examples of how it has been useful for multiple sciences. Contemporary workflows, I like to call them high-dimensional heterogeneous workflows. And when I say high-dimensional heterogeneous workflows, I'm not necessarily referring only to the fact that we are running them in different architectures, but I'm referring to all the different dimensions that can be heterogeneous, such as the data that can be coming from different sources with different formats. It can be regular or irregular. The communication patterns or systems that we're using, not only we use MPI within the simulation itself, but we can also use RPCs or Globus transfer, for example, between facilities. The programming models, again, MPI is perfect for simulations, but it's not necessarily the best one when it comes to big data analysis. So there are other programming models that we're using. And then the orchestration. So sure, in the very old times, we used to have very static orchestration of our workflows where, sure, we have simulation generating data sent to disk and then read back for post-processing and visualization. Right now, we're talking more about dynamic orchestration, and with the agentic components in the picture, we're talking about autonomous orchestration. And finally, we're not running these workflows in single facilities. We can have part of them running in remote facilities, such as the Advanced Photon Source at Argonne, and some of them are running in the high-performance computing facility. And with this heterogeneity come a lot of challenges, such as, well, the resilience challenges we used to have. A node might fail, and I lose the data that has been generated by the instrument. The cross-domain requirements. So I am running part of my workflow at Argonne. Part of it is running on Oak Ridge. And if I need to send the data between these two facilities, it's going to be a little bit complicated. The heterogeneity when it comes to coupling components, either the simulation with data analysis or with other components in autonomous labs, for example. And then with this new creative part here as the agentic component, we're having a lot of other problems, such as the hallucinations we might have, the inconsistencies in the reasoning, the math errors, and so on. So we're having reliability issues as well that we have to deal with. And then when it comes to trying to understand the performance of the end-to-end workflow, this is not very easy either. So at Argonne, I work on workflows in general. That's how I call it. Data management more specifically. And I focus in the last year on three aspects that are the resilience, the performance characterization, and the trustworthiness of these systems. So in this talk, I'll have three sections. So the first one is going to be about the performance characterization. The second one is about resilience and how we can have it as a built-in feature into our workflows rather than as an afterthought. And the third one is how we can enable reliability or trustworthiness in a creative, also known as agentic systems. So with that, I start with the first section. So we cannot improve what we cannot measure. And you'd say that, but we have been doing that for ages. We're still talking about that. Well, sure. And we had the talk from Ruud last time about the trace, and that's great. But the way you think about it with this heterogeneity is that we're having multiple architectures, multiple components, multiple languages, and so on. And these will mean that we're going to have different profiles, different counters, and different traces and behaviors for each component. And you're going to have different tools to collect these data for each of them. And then when it comes to correlating all these data that you get from different layers or different tools, it is extremely hard. So the way you think about it is that there is a characterization gap, which is these workflows behave holistically, but these tools actually study them in shards. So how can we study these workflows as end-to-end processes? So we came up with these multi-layer observability system where we not only consider the system-level metrics, which is here, either the IO behavior of the application, the CPU behavior, all you can get from your GPU metrics, and so on. So we wanted to have multiple layers and include both the workflow management level layers and the job level layers. So with that, we're going to add, from the workflow management level, we're going to add coarser granularity aspects to our performance and provenance layers, such as the task creation and all task-related behaviors, such as the transitions, the task inputs and outputs, and the work stealing, for example, that is a common behavior in dynamic systems and so on. And also the job level, which include the configurations, the logs that we might have from our runs that include very important information about how the runs went. And finally, when we have all of these data, we'd like to correlate it, and we want to have it in a very easily searchable format. So an example of how tricky or complex it can be is through this Darshan tool. So Darshan is a very known HPC I/O characterization tool, and it has been used for ages for MPI simulation, and it works perfectly. So the way it works is that it associates a log for every MPI process, and again, in MPI simulation, that would make sense, and it will give us enough information to understand the I/O behavior of our application. So when we try to understand other type of workflows, and here it was Dask workflows using Darshan, that wasn't that easy, and it was funny that, again, that's normal that we're going to have one log per process. A process in Dask is going to be called a worker, and because we're talking about a task-based system, then these workers are going to execute different tasks. So now we're going to find ourselves with a mapping of M tasks to N IOs, but we don't have a way to map these IOs to every single task or which task generated this type of IOs. So that we had to kind of augment the DXT or Darshan extended tracing tool with more metadata, such as the thread ID and the timestamp, so that we can correlate the low-level I/O records with the task level data, which is a bit high level. And another challenge is that we cannot necessarily study these workflows the same way we used to do for, again, traditional just MPI simulations. And this is a very simple example here, is that, okay, we're going to try to find the number of task graphs, tasks, and so on, and then the number of IOs as well, and the number of transfers. But then it's not a number, it's an interval, because these systems are dynamic. So the number of transfers would depend on the decisions that these runtimes decide at runtime. So studying the variability of these systems becomes a little bit tricky. And another example is this figure in there, where we separate the IO, the communication, the computation, but it doesn't mean anything because it doesn't tell me anything about the system itself. And then to give an example of what we could get from the multi-layer performance characterization tool we developed is this figure here. So this figure presents a parallel coordinate. So here is the elapsed time step. The second one is the type of the task. The fourth and the fifth are the interesting ones here. So this is the task size, so the data produced by these tasks, and finally the duration. So, and then in the other side, we have the distribution of some warnings from the scheduler, and we are interested more in the pink ones, which is event loop unresponsive, or mainly it means that the workers are not responding to the scheduler, and the scheduler is complaining. So mainly what we can look at here is that, oh, these tasks that are taking so long, the red lines, so there are other lines, but we don't see them here because they are just invisible. Because of the color. So the longest tasks are tasks that are very big in terms of size compared to the size that is recommended by desk, which is 128 megabytes, and here we are up to 2 gigabytes. And then most of them, they are all going to this type of task, which is the red packet. So there are IOs in there. And then, interestingly, these tasks are spawned in the first 500 seconds of my workflow. And then a beautiful correlation is driven here, and where I can see all these event loop unresponsibles from our workers, which means that these workers are mainly running very long-running tasks, and they are becoming irresponsive to the scheduler. And without having the whole data that I collected from different layers, I wouldn't be able to understand what's going on with the workers and why the scheduler is complaining. So that was part of a project I was working on, and while doing it, I discovered that Oak Ridge was working on a similar thing, so we just fused our efforts into this tool called Flowcept, which is led by Ren and Souza at Oak Ridge. And mainly, it's just a lot of plugins to different systems, and you can add whatever type of profiler you want, and then all this data is streamed to servers, and then from there you can aggregate the data and analyze it, and you can even have some Grafana dashboards and also agents to query and analyze this data. So great, now we have these workflows a little bit more characterizable. But that's not enough to survive in this world of very contemporary and heterogeneous workflows. So the second part of this talk is going to be about resilience as a built-in feature. And there we focus more on experiment-driven workflows where you have data that is collected from some instruments. So the way it works is that you're going to write a proposal, you wait a couple of months, and then you get access to these instruments to run your experiments, and then you collect your data, you analyze it, and so on. So you cannot necessarily afford, if you lose the data or any of your component crashes, then you will have to do that, and you will have to lose a couple of months of without doing any science, mainly. And then the second point is that most of the pipelines are written or coupled through, at least the one I worked with, is coupled through 0MQ, so it's very tightly coupled and very fragile under load. So mainly if it crashes, if one component crashes, then all of them would crash, and we don't want that. So in this project, we wanted to add an extra layer of resilience to these type of workflows through what's called persistent streaming. And the way you think about it is literally a data movement and communication model that persists, logs the messages between the different components. So that brings the extra layer of resilience, in which case, if a component crashes, you still have the stream, so you can still connect back this component and read back the stream and continue your workflow. The decoupling is very important, so the producers and consumer can operate independently in time and scale, so that's great. And then the elasticity, which means that they can join and leave the stream whenever they feel like it or they crash. In our use case, which is a tomographic reconstruction workflow, and you can think about it as as when you're injured and you have an X-ray. So mainly there is the object that you want to study sitting on a rotating stage. From the side you have the X-ray source. In the other side you have the detector, and then the X-ray is shooting. The detector is detecting projections, and these projections are sent to a local workstation where if the projections are considered the vertical cats of the object, then the sinograms are the horizontal ones. So once you construct these sinograms, you send them to an HPC facility, hopefully, to be reconstructed for the tomographic reconstruction process, which is very parallelizable and very heavy in computation. And then once this is done, you are going to have the images or the 3D volumes as well that are very big in size, and you can save them in parallel file systems or any other storage. So the original version of this workflow was coupled through 0MQ. So it was very synchronous, tightly coupled, and if it fails, it fails. So in this project, which is called Diaspora, that I think you mentioned, of course you did. So we developed two persistent streaming solutions. So the first one is Octopus. I'm not going to talk about this one. It's a cloud-based solution, so mainly it's ideal for a cross-facility type of streaming. And then the second one is Mofka. This one I'm going to talk about, is tailored for HPC platforms. So this work has been led by Mathieu Dorier, and Mofka is built on top of Mochi, and Mochi is a set of tools and methods to build services for HPC data and big data and large-scale learning. So Mofka is the persistent streaming service of Mochi, which is very analogous to Kafka, but fully tailored for HPC architectural features. So it leverages RDMA, multi-cores, and so on. In Mofka, events have two parts, data and metadata. So the data part is sent through RDMA. The metadata are copied in the system, so we suppose that they are very small. And they are organized into topics. And these topics might have different partitions or multiple partitions if you want to scale the system. So in terms of architecture, mainly the way you can think about it is that you have a producer, you have a consumer up there, and then these two can be very customizable. So you can create your own validator of the data, selector, and serializer. So the producer produces events that are both data and metadata, as I mentioned, and these events are sent into the servers. So these servers are, because they are built on top of Mochi, they are very composable and elastic, so you can add servers if needed. And finally, the consumer can connect to the server and get the data from it. So we used Mofka to rewrite or reinvent the original workflow I was mentioning. So these are the different components that I had at the beginning, and then in the middle we have these Mofka servers, which is the extra layer for resilience. So mainly every direction of communication between the different components, which is, for example, here we have one communication, we're going to have an associated topic in the servers. And if we have parallel components, such as the reconstruction algorithm in here, we can have multiple partitions per topic, so we're going to distribute perfectly the load in the server as well. Something to say is that this architecture, as you can see, is fully decoupled, so they are not dependent on each other. They can connect and disconnect whenever they feel like it. It's elastic and, as I mentioned, scalable by design from Mochi. To double what I was mentioning about the high dimensional heterogeneity, these are the characteristics of the workflow. So in terms of programming languages, we have Python, we have C++, we have also C, I didn't mention it here. We have MPI and OpenMP as a programming model, and TensorFlow for one of the analysis components. In terms of scalability, so some of them are running in one node, some of them are running to up to 32 nodes. In terms of type of data, so we have projections, we have sinograms, the sizes are different, and we have reconstructed 2D images as well. So you can have anything you want, and it doesn't add any complexity to add more components to your workflow. In terms of performance, so that's a comparison between Mofka and 0MQ, and as you can imagine, we have better performance than 0MQ for reasons I mentioned already, and the fact that Mofka leverages the HPC architecture perfectly. So we have at least 12x reduction in the overall overhead across all the components. And when I say overhead, it's literally the components without streaming versus the component with streaming. Sometimes we have up to 500x better than 0MQ, and this is specifically in the case of the component that generate the reconstructed data, which is huge. It's up to 25 megabyte. I need water. Megabyte per image. And yeah, and sometimes we even noticed smaller than around a complete round trip, RPC round trip in Polaris, and Polaris is the system where we run this performance in. And that's due to the fact that we actually buffer the data and we don't send it. So we don't have that overhead in this data. Sure. So I will skip then these performance results, but I can go back if needed and skip to the last section. So now that we talked about the resilience, the way we know it, which is maybe a component failing or a network is not responding and so on, let's talk about enhancing the trustworthiness or the reliability in agentic workflows. So before talking about agentic workflows, maybe we should talk about agents. So they are not new. They have been introduced first, at least the latest the earliest I found is 1999. I was 4 by that time. And so the way you can think about it is as is an entity that has 4 main components: a brain, a memory, perception tools, and action mechanisms. And for each of them, there are a lot of problems. So the brain might hallucinate. It might have inconsistencies in the reasoning. It might generate math error because it's just predictions. It doesn't do math. The memory might be restricted in terms in size, in relevance, and so on. Sorry. And when we incorporate these agents into the traditional workflows, we have what is called agentic workflows. So the way we think about the reliability aspect here is literally just defining a new type of fault, which is not necessarily a component crashing, but it's mainly a component which is failing in a different way, which can be a hallucination, as I mentioned, which can be a math error. And the resilience that we would talk about here is bringing back the system into a more reliable state. And that is important because if, for example, this agent says that 3 is greater than 5, and this data is propagated through the whole workflow, then it's going to be problematic, and multiple tasks and agents are going to be contaminated by these errors. So the way we think about it is that we'd want to detect, contain, and be able to recover from these failures in our workflows if we want to use them for science in any way. So we came up with this two-layered reliability framework for agentic systems where we not only focus on reliability aspects for a single agent, but we also extend that to the whole workflow because the agents are not acting separately in the workflow. And I'm not gonna go into details in this slide, but I focus only on the provenance part. So part of these mechanisms is being able to capture provenance for what's going on within the agent and the full workflow. And this has been also focused on the Genesis mission. So we extended the WC3C prov to include IA agent into the whole workflow provenance by, and that's here, by incorporating all the data that can be associated with an IA agent, such as the invocation of tools, the IA model that is invocated, the prompts, the responses, the reasoning models, the reasoning traces, the type of the model, the temperatures, and so on. And that has been incorporated again to the tool I mentioned, which is FlowSept, and that's on the AI agent part. So that's also part of the data we capture and stream to our streaming hubs. And as I mentioned, so there are different tools to persist the provenance and then query it and analyze what's going on in the system. And with that, I'm getting to the conclusion. So in this talk, we've presented 3 challenges, and I don't like to call them solutions, but I call them usually coping mechanisms with contemporary workflows. So performance characterization, how it can be augmented to serve these workflows as end-to-end instruments for science. How we enabled resilience as a built-in feature through persistent streaming in real-world use cases, such as the tomographic reconstruction workflow. And finally, talked a little bit about agentic reliability and our 2-layer reliability framework to make these agents more reliable for science. And with that, I'd like to conclude with these questions, which I'm not going to read. Otherwise, Nicholas will be mad at me. So thank you all for your attention. And if you have questions, please feel free to ask.